On June 7, 1944, the day after D-Day, the Panzer Lehr Division received orders to move toward Normandy. It was one of the finest armored formations in the German military, built from the instructors of Germany's tank schools, the professional elite of a professional army. Its equipment was the best Germany had: Panzer IVs, half-tracks, and above all the new Panther, the medium tank German engineers had designed to be superior to any Allied armor. The Panther was superior in almost every measurable way. Its 75mm KWK-42 gun, a long, high-velocity weapon with a muzzle velocity of 935 meters per second, could penetrate the frontal armor of a Sherman tank at ranges exceeding 1,000 meters. The Sherman's 75mm gun could not reliably penetrate a Panther's frontal armor at any combat range. The Panther's sloped armor, inspired by the Soviet T-34, deflected shells that would have penetrated vertical plates of the same thickness. Its optics, Zeiss lenses of the kind that had made German cameras the finest in the world, gave its gunners targeting capabilities that Allied tank crews envied. On paper, the Panther was the most formidable medium tank of the war. General Fritz Bayerlein, commanding Panzer Lehr, had served under Rommel in North Africa and commanded armor on the Eastern Front. He knew what a good tank felt like and what a problematic one felt like. The Panthers felt problematic. The division's march to the Normandy front covered approximately 200 kilometers of French roads, not combat, not enemy fire, simply driving. By the time the division reached the front, approximately half of its Panthers had broken down. Not half destroyed, half broken down. Engine failures, transmission failures. The final drive, the mechanism that transferred power from the transmission to the tracks, failing at rates that Bayerlein described in his reports with the controlled fury of a man who had been handed a weapon that did not work. This was before the first contact with American forces, before a single shell had been fired. The Panthers that American soldiers would later find abandoned, some destroyed by enemy action, some simply left where their engines had given out, were these Panthers. The tank designed to be the best medium tank in the world, breaking down at a rate that made it, in campaign conditions rather than on a test track, something less than what the specifications promised. The American soldiers who first encountered abandoned Panthers in the hedgerow country of Normandy were not immediately certain what they were looking at. They climbed up and looked inside. What they found would produce reports that made their way back to the United States Army Ordnance Department, to the Aberdeen Proving Ground in Maryland, and eventually to the desks of the engineers responsible for understanding German armor. The reports described, with the specific attention of men who maintain machines for a living, what German engineering had produced. It was magnificent. It was also the wrong answer to the wrong question. The right question: what tank can we build in the numbers we need, maintain in the field with the mechanics we have, and keep running for a war that will last years? The Panther answered the first question. The Sherman answered the second. Bayerlein's broken-down Panthers on the road to Normandy were the gap between those two answers made visible. Excellent on the test track, unreliable on the road to the front, superior in the duel between two tanks in a field, absent from the battle because the transmission had failed 50 kilometers back. The American soldiers climbing into the abandoned Panther in the hedgerows of Normandy did not know Bayerlein's march statistics. They knew what they saw: a tank that was more sophisticated than anything they had trained on, with a gun that could kill them from distances their own weapons could not match, sitting abandoned in a French field because something inside it had stopped working. They were about to find out what. What they found would tell them more about why Germany was losing than any battle report. The Panther's problems began with its wheels. The Panther's running gear used an interleaved wheel system, multiple rows of road wheels overlapping each other, designed to distribute the tank's weight more evenly. In theory, it improved ride quality. When mud packed into the interleaved wheels and froze, as it did in the autumn mud of Normandy, the entire running gear could seize. Clearing it required removing the outermost row of wheels, hours of work, tools that field conditions rarely provided. When the tools were not available, the tank stayed where it was. The running gear was unlike anything on a Sherman, more complex, more elegant in a theoretical sense, and conspicuously more difficult to work on. The engine was the second thing. The Panther's Maybach HL230 engine produced approximately 700 horsepower, smooth-running, powerful, capable of moving a 45-ton tank at speeds that surprised Allied crews. It also caught fire. The fuel pumps, carburetors, and fuel lines on early Panther models were prone to leakage. Gasoline would pool in the engine compartment. When the tank climbed a slope, the pooled fuel would slosh onto hot engine components and ignite. When Panthers were being gathered for operations in 1943, 2 were destroyed by engine fires before they had fired a single shot in anger. The Sherman had acquired a reputation as a fire trap. German crews called it the Tommy Cooker, American crews the Ronson. The reputation was not entirely undeserved. Shermans did burn when penetrated, but Panthers burned more often. Not from enemy fire, from their own fuel systems, from the mechanical complexity that created failure points that simpler designs did not have. American mechanics examining the captured Panther's engine compartment found the evidence of this. The fuel line routing, the carburetor placement, the proximity of flammable components to hot engine surfaces. They understood what they were looking at. What they were looking at was a machine engineered for peak performance under ideal conditions. The conditions of a campaign in France in the summer of 1944 were not ideal. The transmission was the third thing. The Panther's 7-speed synchromesh transmission was sophisticated. Drivers who mastered it could extract impressive performance. Mastering it took time and skill. When a transmission failed, and they failed regularly, especially the final drive that translated the transmission's output into track movement, the repair required removing the engine. Removing the engine from a Panther required a crane and approximately 16 hours of labor by trained mechanics under good conditions. Field conditions were not good conditions. On a Sherman, an experienced crew could replace the engine in the field in approximately 4 hours using the tank's own tools. The Sherman had been designed to be fixed by the men who operated it, in the conditions they would be operating in. The Panther had been designed to be superior. The Sherman had been designed to be maintained. These were different objectives. The American mechanics who produced these reports were sergeants and lieutenants with grease under their fingernails, trained to keep vehicles running. They noted the interleaved wheels, knowing how long wheel replacement took on a Sherman. They noted the fuel line routing, having seen what happened when fuel met hot metal. They noted the transmission, understanding that what had been a 4-hour job would be a 16-hour job, if the right tools were available, which in the field they often were not. Their reports went up the chain of command. They were read by engineers at Aberdeen who added the field observations to the systematic testing they were conducting on a captured Panther that had been shipped back to Maryland. The Panther was magnificent. It was also unmaintainable under campaign conditions. And an unmaintainable tank, however magnificent, was a tank that sat in a French field waiting to be captured. The Aberdeen Proving Ground in Maryland was where the United States Army sent things it needed to understand. Captured German tanks, Japanese aircraft, Italian artillery, the material of the enemy's arsenal, evaluated by American engineers with the systematic attention that professional ordnance work required. The facility had been operating since 1917, and by 1944 it had developed the specific expertise of an institution that had seen many weapons and understood how to extract the information that mattered. In the summer of 1944, Aberdeen received a Panther. The tank had been captured in France. One of the Panthers abandoned during the Normandy fighting, recovered by American forces, and shipped back to the United States for evaluation. It arrived at Aberdeen intact enough to be driven, which was more than could be said for many of the Panthers that American forces encountered in France. The engineers who received it were not unfamiliar with the Panther. Reports had been coming in from the field since the first encounters in Normandy. The systematic testing at Aberdeen was the opportunity to go beyond what field mechanics could observe in a hedgerow and apply the full resources of the proving ground, the instrumented test tracks, the specialized measuring equipment, the trained evaluators who could quantify what field reports could only describe. What they found confirmed the field reports and added detail. The Panther required approximately 55 hours of maintenance per week to keep operational. Not repair, maintenance. The scheduled servicing, the lubrication, the inspection, and adjustment that had to be performed continuously to prevent the mechanical failures that would occur without it. The Sherman required approximately 17 hours of maintenance per week. The difference, 38 hours per week, was not an abstraction. It was the specific, practical cost of the Panther's engineering philosophy in time and labor. A Panther required 3 times as much maintenance as a Sherman. In a unit with 20 Panthers, this meant the equivalent of a full-time maintenance crew working around the clock to keep the tanks in the field. The German Army had such crews. German tank maintenance battalions were professional, skilled, and equipped with the specialized tools that Panther maintenance required. Under ideal conditions, adequate time, proper facilities, the right parts, they could keep Panthers running. The Normandy campaign did not provide ideal conditions. The Panther's engine, the Aberdeen engineers found, required replacement at intervals that would have seemed extraordinary to anyone accustomed to American standards. Early production Panthers averaged fewer than 150 kilometers between major drivetrain failures. Even later, improved models had engines with service lives of approximately 1,000 kilometers before they required major overhaul. For context, a Sherman engine, under comparable conditions, could run for 3,000 to 4,000 kilometers before requiring major service. The Panther's engine lasted roughly a quarter as long. This meant that a Panther operating in a mobile campaign, moving 30 or 40 kilometers per day as the Normandy fighting required, would need engine maintenance after approximately 3 weeks of active operation. In a static defensive position where daily mileage was lower, the engine life stretched further. But the Normandy campaign was not static, and the German forces responding to the Allied breakout were not operating in static positions. They were moving, and as they moved, their Panthers were dying. Not from American guns, though American guns were killing them too. From their own engines, their own transmissions, their own mechanical complexity, failing at the rates that the design and the conditions had made inevitable. Colonel Alonzo Fox, one of the senior ordnance officers evaluating the captured Panther at Aberdeen, had a specific professional vocabulary for what he was seeing. It was the vocabulary of a man who had spent his career evaluating weapons not for their peak performance, but for their sustained performance. Not what they could do in optimal conditions, but what they could do in the conditions that war actually provided. The Panther's peak performance was exceptional. Its sustained performance was not. And in a war that was decided not by peak engagements, but by sustained operations over months and years, sustained performance was the number that mattered. Fox's evaluation reports used numbers because numbers were the language of ordnance assessment. But behind the numbers was something that the numbers alone did not fully capture, a quality of engineering philosophy that the Panther embodied and that the Aberdeen evaluation made legible. The Panther had been designed by engineers who asked, "What is the best tank we can build?" It was the right question if you were building 1 tank, or 10, or 100. It became the wrong question when you needed to build thousands, and then tens of thousands, when the factory floor, not the drawing board, became the limiting constraint on what was possible. The Panther's hull required precise machining tolerances that slowed production. Its interleaved wheel system required components that simpler designs did not. Its transmission required skilled assembly that could not be learned in weeks. Each of these choices had been rational at the point it was made. Each had contributed to the tank's performance envelope. Together, they created a vehicle that the German industrial economy, already stretched by the demands of a war on multiple fronts, could produce only in limited numbers. In 1944, German factories produced approximately 3,740 Panthers. In the same year, American factories produced approximately 17,565 Shermans. Fox knew these numbers. They were part of the intelligence picture that Aberdeen's evaluations fed into, the broader assessment of German versus Allied industrial capacity that shaped strategic planning at the highest levels. But the numbers acquired a different texture when you were standing next to an actual Panther. looking at the specific engineering choices that had produced them. The interleaved wheels, the Maybach engine, the 7-speed transmission. Each had been chosen for a reason. Each reason had been sound. And each choice had added cost, complexity, time, on the factory floor and in the field, that a simpler design would not have incurred. The Sherman's simplicity was not an accident. It was a choice. American engineers designing the Sherman in 1940 and 1941 had made decisions that their counterparts in Germany had not made. Decisions to sacrifice peak performance for maintainability, to accept a less sophisticated running gear in exchange for one that could be serviced without specialized tools, to build an engine that lasted longer at the cost of producing less power per liter. These decisions had looked like compromises. In 1944, examined against the background of what German engineering had produced, they looked like engineering judgment of a different kind. Judgment about what a weapon needed to do not in the best case, but in the sustained case. Aberdeen's evaluation included firing tests. The Panther's gun, the long 75mm KWK-42, performed exactly as the specifications had promised. At ranges of 500 meters, 800 meters, 1,000 meters, it penetrated armor that the Sherman's gun could not touch. The optics were superb. The gun's accuracy at long range was better than anything in the American inventory. The Sherman's gun, tested against captured Panther armor at the same ranges, told a different story. Against the Panther's frontal armor, 80 millimeters of sloped plate, the Sherman's 75mm gun was essentially ineffective at combat ranges. The armor held. This was the number that American tank crews in Normandy had already discovered empirically, and discovering it empirically, from inside a burning Sherman, was a different experience than reading it in an Aberdeen evaluation report. Fox documented it without editorial comment. It was his job to document, not to editorialize. But the documentation itself carried weight. A gun that could not penetrate an enemy tank's frontal armor was a gun that required different tactics, flanking approaches, waiting for the shot that would find thinner side or rear armor, accepting engagement ranges and positions that placed American crews at disadvantage in exchange for the shot geometry that made penetration possible. American tank tactics in Normandy had evolved to account for this. The tactics were not elegant, they were costly. They worked because American forces had more tanks, more replacements, and more fuel than their opponents, because the system behind the Sherman was larger than the system behind the Panther. And in a war decided by systems rather than duels, the larger system was the winning one. Fox's report concluded with a section that the Aberdeen evaluations always included: overall assessment. The Panther was the finest medium tank of the war on the dimensions it had been designed to excel on. It was not the finest medium tank of the war on the dimensions that the war had turned out to require. The war had required not the finest tank. The war had required enough tanks, maintained, fueled, armed, and present at the point of contact, to outlast an opponent who had built something better and fewer of it. The Sherman was enough. The Panther was better and insufficient. Fox filed his report. The war continued. Private Edward Cole of the 2nd Armored Division found the Panther on June 11, 1944, 5 days after the landing. The tank was sitting on the shoulder of a road between St. Lo and Bayeux, tilted slightly toward the ditch. The turret was traversed to roughly 2 o'clock. The hatches were open. There were no signs of a hit, no penetration holes, no scorching on the armor, none of the smell of burned metal that Cole had already learned to identify at a distance. The tank had simply stopped. Cole was a driver-mechanic on an M4A1 Sherman, and he had the habit of looking at machinery the way men who fix things look at it, which is to say, with the question, what went wrong here, and how long will it take to fix? He walked the perimeter. The running gear was unlike anything he knew. On the Sherman, 5 road wheels per side, arranged in a single row, a straightforward layout that Cole could disassemble and reassemble in the dark. On the Panther, the wheels were arranged in multiple overlapping rows, a dense interlocked system that had already collected a substantial amount of Normandy mud in its gaps. Cole crouched and looked more carefully. He could not immediately see how the mud would be cleared from the inner rows. There was no obvious access. He climbed up onto the hull. The tank was larger than a Sherman, noticeably larger, with the kind of confident mass that reads as power on a test track and as a liability in the narrow Norman bocage. The gun barrel extended forward at a length Cole noted professionally. A gun that long would snag on branches, restrict turret traverse near walls and hedgerows, create problems in exactly the terrain the division had been fighting through for 5 days. He looked down through the open commander's hatch. The interior smelled of machine oil, leather, and something else. Cole took a moment to identify it, and then recognized it as quality. Not the price of the thing, but the precision of its manufacture. The instrument panel, the control levers, the sighting equipment, all of it built to tolerances that in an American workshop would have been called exceptional. The Zeiss optics on the gun sight gave a magnification and image clarity that made Cole stare through the eyepiece for several seconds before he remembered why he had climbed up. Then he opened the engine access panel. The engine was dead. Not knocked out, mechanically dead, with the specific finality that an experienced mechanic senses before he can articulate it. Cole examined the fuel lines. One had failed, a small leak, but sufficient to drain the system over several hours of movement. The fuel had gone. The engine had stopped. The crew had walked away. That was all. No battle. No American shell. A tank that had cost, Cole did not know the exact figure but assumed it was considerable, was sitting in a Norman ditch because of a leaking fuel line. He climbed down and lit a cigarette. That same afternoon, Lieutenant James Harris of the same unit filed a preliminary report on the abandoned Panther. The report used standard military language without commentary, listing observations in the order they had been made: running gear, engine, armament, optics, ammunition status. The report went up the chain. Over the following 2 weeks, American units found several dozen more abandoned Panthers, in varying condition, with varying causes of failure, but with one consistent characteristic. Most of them had not been destroyed in combat. They had stopped on their own. The officers reading these reports in the divisional headquarters made notes. The engineers who received them at Aberdeen were already composing the list of questions they intended to answer with the Panther that was on its way to Maryland. The Panther that reached Aberdeen in late July 1944 had been recovered from a field outside Caen. It had been towed out by an M32 tank recovery vehicle, a Sherman hull converted for the purpose, which required 2 attempts because the Panther's weight exceeded what a single M32 could comfortably manage on soft ground. The logistics of moving a broken German tank from a Norman field to a ship at Cherbourg, and then to a proving ground in Maryland, were not trivial. The Army Ordnance Department had decided they were worth it. Colonel Alonzo Fox was at Aberdeen when the tank arrived. Fox had spent his career in ordnance, the branch of the Army responsible for weapons procurement, evaluation, and maintenance standards. It was work that attracted a particular kind of officer, methodical, skeptical of claims that could not be measured, more interested in what a weapon did over 1,000 rounds than what it did on the first shot. Fox had evaluated captured Italian armor in North Africa and German equipment recovered in Tunisia. He approached the Panther with the same systematic attention he had applied to all of it. The first thing his team did was drive it. The Panther ran. The engine started after some difficulty. The fuel system required attention before it would turn over consistently, but once running, it moved with a smoothness that surprised the American drivers who took it around Aberdeen's test track. The transmission, when operated correctly, was precise. The steering was responsive. At speed on a flat surface, the Panther felt like what it was, a well-engineered machine performing near the top of its design envelope. Fox's team drove it for 3 days before they began the systematic disassembly. What the disassembly revealed confirmed and extended the field reports. The interleaved wheel system, examined off the tank, was a piece of engineering that the Aberdeen staff could appreciate on its own terms. Clever, effective at distributing load, genuinely superior to simpler designs in the specific problem it was solving. It was also a system that required removing the outer wheel row to access the inner components, a process that took trained mechanics with the right tools approximately 4 hours per side. On a Sherman, wheel replacement was a job for 2 men and an afternoon. On a Panther, it was a job for a maintenance platoon and a full day, under field conditions that rarely provided the clean workspace and complete tool set the job demanded. The fuel system told a similar story. The routing of the fuel lines, the placement of the carburetors, the proximity of flammable components to exhaust heat. Fox's engineers documented each decision with the specific notation of men who understood why the decisions had been made and what they cost. The decisions had been made to optimize performance. The cost was a system that required careful, regular attention to prevent the leaks and pooling that led to fires. The gun they saved for last, the KWK-42, the long 75mm that was the Panther's primary reason for existing, was tested against standard American armor plate at ranges from 200 to 1,500 meters. The results were not surprising. They had been anticipated by the field reports, by the intelligence assessments, by the accounts of Sherman crews who had survived engagements with Panthers at various ranges. The gun was exceptional. At 1,000 meters, it penetrated armor that no American tank gun in the inventory could touch at the same range. Fox documented this without alarm. The purpose of the evaluation was not to determine whether the Panther was dangerous. That had been established in Normandy, but to understand precisely what it was dangerous with, and what it was not. What it was not. A weapon system that could be sustained in the field at the numbers the German army needed. The evaluation report that Fox filed in September 1944 ran to 47 pages. Its conclusions were carefully worded, as Aberdeen conclusions always were, specific, qualified, supported by the test data that occupied the report's appendices. The summary was 4 sentences. The Panther is the most capable medium tank encountered in this theater on the criteria of firepower and protection. Its mechanical reliability under field conditions is substantially below American standards. Maintenance requirements exceed what German field logistics can consistently provide during mobile operations. Its tactical superiority in individual engagements does not compensate for its operational unavailability. Fox signed it and sent it up. The number was 6,000. That was approximately how many Panthers Germany produced during the entire war, from the first units that arrived at Kursk in July 1943 to the last vehicles assembled in the final months of 1945. 6,000 tanks over roughly 2.5 years of production, from factories that were being bombed with increasing regularity by the time the Panther reached full-scale output. The other number was 49,234. That was how many Shermans the United States produced during the same period, and that figure did not include the additional thousands built for the British Army under Lend-Lease, which brought total Sherman production across all variants to approximately 50,000. Fox kept both numbers in his head when he was writing his evaluation report. They were not the only numbers that mattered. A production comparison between Germany and the United States was not a fair comparison in isolation. Germany was fighting on multiple fronts simultaneously, allocating industrial capacity across aircraft, submarines, artillery, and a dozen other competing demands. The Panther was not competing only against the Sherman. It was competing against everything else the German war economy needed to produce. But the numbers were real, and their implications were real. 50,000 Shermans against 6,000 Panthers meant that even if every Panther destroyed 5 Shermans before being knocked out, a ratio that exceeded what the actual combat record showed, the arithmetic still favored the Sherman. The exchange rate required to make the Panther's qualitative superiority strategically decisive was higher than the Panther could achieve. This was not a new insight. Military historians had been making versions of this argument since Napoleon. Quantity has a quality all its own. The phrase was attributed to various commanders, possibly apocryphally, but the underlying logic was older than any of them. A weapon that could be produced in sufficient numbers to be present at every engagement was more useful than a weapon superior in every engagement it could actually reach. The Panther could not reach all of them. The production mathematics explained part of why. The maintenance mathematics explained the rest. A Panther required approximately 150,000 man-hours to produce. A Sherman required approximately 50,000. The difference, 100,000 man-hours per tank, was the specific cost of the Panther's engineering complexity on the factory floor. Every hour spent on the additional machining tolerances, the more complex components, the tighter assembly specifications, was an hour not spent building a second or third Sherman. German factories were not inefficient. Albert Speer's rationalization of German war production after 1942 had achieved genuine improvements in output. Panther production in 1944 was higher than it had been in 1943, despite the bombing campaign. The German industrial workforce was skilled and motivated. They were also building the wrong thing, in the sense that what they were building could not be built in the numbers the strategic situation required. American factories in Detroit and Ohio and Pennsylvania were building something different. The Chrysler plant in Detroit, converted from automobile production to Sherman assembly, was producing tanks at a rate that German intelligence found difficult to credit when the figures were reported. The assembly line methods that Henry Ford had developed for automobiles had been adapted for tank production with a pragmatic efficiency that prioritized throughput over perfection. A Sherman that came off the line was not the finest tank that American engineers could have built. It was the finest tank that American engineers could build 50,000 of. The distinction was the war. Fox had visited the Chrysler plant before his assignment to Aberdeen. He had stood on the production floor and watched Shermans move down the line, hull, then engine, then turret, then the final assembly checks, at a pace that had no equivalent in German production. The workers were not specially trained machinists. Many of them had been building automobiles 18 months earlier. The Sherman had been designed so that they could build it. The Panther had been designed so that it would be the best tank in the world. Both objectives had been achieved. Only one of them had been the right objective. The production gap had a second dimension that the raw numbers did not immediately reveal. It was not only that America built more Shermans than Germany built Panthers. It was that America built them faster, replaced them faster, and absorbed losses at a rate that German planners had not fully anticipated when they had calculated what the war in the West would require. In the summer of 1944, an American armored division that lost 20 Shermans in a week's fighting could expect replacement vehicles within days. The logistics chain, from factory to port to ship to beach to depot to unit, had been built with the same systematic attention to throughput that had designed the Sherman itself. The vehicles moved because the system had been designed to move them. A German armored division that lost 20 Panthers in the same week faced a different calculation. Replacement Panthers existed, production had not stopped, but the logistics chain that delivered them to France was operating under Allied air superiority that made daylight movement of heavy equipment extremely costly. Trains were bombed, road columns were attacked. The Panthers that existed in the depots east of the Rhine moved toward the front at night, in fragments, arriving in ones and twos rather than in the battalion-strength replacements that a division's order of battle required. The operational consequence was asymmetric attrition. Both sides were losing tanks. The Americans were replacing theirs. The Germans were replacing theirs more slowly, with vehicles that required more maintenance, along supply lines that were increasingly interdicted by the same air power that was making the Panthers' daylight movement dangerous. Fox's report addressed this indirectly. It was an ordnance evaluation, not a logistics assessment. But the implication was present in the numbers he had compiled. A tank with a 150-kilometer mean distance between drivetrain failures, operating 60 kilometers from its nearest maintenance depot, would require recovery and repair within the first 2 to 3 days of active operations. A tank with a 3,000-kilometer engine life, operating in the same conditions, would not. The Sherman's reliability was not glamorous. It did not appear in the specifications as a headline figure. It did not make the tank more impressive in the kind of comparison that tankers made when they were talking about what they would rather be fighting in. Every Sherman crew in Normandy knew the arithmetic of the duel. A Panther's gun at 1,000 meters, their armor, the outcome if they met one in open ground. The arithmetic was not favorable. What the crews did not see, because it was not visible from inside a tank, was the other arithmetic. The arithmetic of the maintenance battalion working through the night, the replacement vehicles arriving at the divisional depot, the fuel trucks moving forward on roads that American air power kept open. The arithmetic of a system that had been designed not to produce the finest tank, but to keep the largest possible number of tanks in the field at any given moment. Bayerlein had seen it. Not immediately. In the chaos of the Normandy fighting, causes and effects were difficult to isolate. But by August 1944, as the German position in France collapsed and Panzer Lehr was fighting rearguard actions through the Falaise pocket, the pattern was legible. His Panthers were breaking down. American Shermans were appearing in their place. Not superior Shermans, the same Shermans, or vehicles indistinguishable from them, replacing losses at a rate that Panzer Lehr could not match. He wrote about it after the war. His memoirs describe the Normandy campaign with the controlled precision of a professional who had been defeated and understood why. The American tank was inferior in the engagement. The American army was superior in the campaign. The difference between those two statements was the difference between a weapon and a system, between what a tank could do when it arrived at the battle and what an army could do to ensure that enough tanks arrived at enough battles to decide the outcome. Fox's evaluation had been making the same argument in the language of ordnance assessment. Bayerlein had been living it in the language of operational command. They had reached the same conclusion from opposite sides of the same fact. The question that the Panther posed was not whether it was a better tank than the Sherman. It was. On the criteria that tank designers use to evaluate tanks, firepower, protection, the ability to destroy an enemy vehicle before the enemy vehicle destroys you, the Panther was superior to the Sherman in most engagement scenarios that could be constructed on a test range or a wargaming table. Its gun outranged the Sherman's standard armament. Its frontal armor defeated the Sherman's standard ammunition. Its optics gave its crew an advantage in target acquisition that translated, in the specific geometry of a tank duel in open ground, into a first-shot advantage that was often decisive. None of this was in dispute. Fox's report had documented it. The crews who had fought in Normandy had confirmed it. Bayerlein had not needed to confirm it. He had known it before the first engagement. The question was whether being a better tank was sufficient. The answer, worked out across 11 months of fighting from Normandy to the Rhine, was that it was not. A better tank that broke down on the road to the battle was not present at the battle. A better tank that required 16 hours of crane work to replace its engine was not available for the next day's fighting, while a Sherman with a failed engine was. A better tank produced in numbers that could not replace losses at the rate losses were occurring was a better tank that existed in shrinking quantities, while the inferior tank existed in quantities that stayed roughly constant because the system behind it had been built to keep them constant. The Sherman was not the finest tank of the Second World War. It was the right tank for the war the United States was fighting, a war of sustained operations across a continent, supplied across an ocean, dependent on a logistics chain that had to function for years rather than weeks. A war in which the factory floor was as much a battlefield as Normandy, and in which the ability to keep vehicles running was as decisive as the vehicle's performance when they ran. This was not a lesson that was easy to absorb in 1944, when the men being asked to absorb it were doing so from inside Shermans that could not penetrate a Panther's frontal armor. The lesson required distance, the distance of the operational level from the tactical level, the distance of the historian from the participant, the distance of Fox's evaluation report from the specific afternoon in a Norman hedgerow when an American crew had learned empirically what the Aberdeen tests would later document systematically. From that distance, the verdict was clear. The Sherman had won not because it was superior, but because the system that produced it, supplied it, maintained it, and replaced it when it was lost was superior. Superior in scale, in logistics, in the industrial capacity that converted raw material into finished armor at rates the German war economy could not approach. Bayerlein's Panthers, breaking down on the road to Normandy before the first shot was fired, were the clearest expression of this verdict available. Not the finest armor in the world, failing in combat. The finest armor in the world, failing on the road to combat. The distinction was everything. Fritz Bayerlein survived the war. He was captured in April 1945 in the Ruhr Pocket, surrendering with the remnants of what had once been Panzer Lehr Division, a formation that had begun the Normandy campaign as one of the finest armored units in the German military and ended it as a collection of exhausted men and broken vehicles moving on foot through a Germany that no longer had the fuel to keep its tanks running. He spent several years after the war being interviewed by American military historians, part of the Foreign Military Studies program, which collected the operational assessments of German commanders while their memories were still fresh. The interviews were conducted with professional courtesy on both sides. Bayerlein was a precise witness. He described what he had seen and what he had concluded from it, without the self-justification that characterized some of his contemporaries. On the Panther, his assessment was consistent across every interview. The tank was exceptional. The tank was too complex for the conditions in which it was asked to operate. The two facts coexisted without contradiction because they described different things. The tank's performance envelope on one hand, and the gap between that envelope and what the campaign required on the other. Alonzo Fox returned to civilian life after the war and left no memoir. His evaluation reports remained in the Aberdeen Proving Ground archives, filed alongside assessments of Italian artillery and Japanese aircraft, and the dozens of other captured weapons that had passed through the facility during the war. They were the work of a professional doing professional work, systematic, precise, useful to the people who needed to make decisions, and uninterested in the kind of drama that popular histories later found in the Panther's story. The drama was real. The tank was genuinely formidable. The crews who faced it had genuinely been at a disadvantage in the individual engagement, and the cost of that disadvantage had been paid in specific, irreversible ways by specific men whose names appeared in casualty lists rather than evaluation reports. But the drama of the individual engagement was not the story of the war. The story of the war was the story of systems, of production lines and logistics chains and maintenance battalions and fuel depots, and the 10,000 unglamorous decisions that determined not which tank was better, but which army could keep more tanks in the field for longer. The Sherman was that army's answer to that question. It was not a satisfying answer in the way that the Panther was a satisfying answer. The Panther was the kind of machine that people who care about machines find compelling, pushed to the edge of what the technology of its era could achieve, bearing the marks of engineers who had tried to build the best possible version of the thing they were building. The Sherman was the kind of machine that wins wars. The distinction between those two things, between the best possible version and the version that wins, was not unique to 1944. It recurred in every domain where engineering met operational reality, where the conditions of use differed from the conditions of design, where the question was not what a system could do in optimal circumstances, but what it could do in the circumstances that actually existed. The Panther answered the question it had been asked. The Sherman answered the question that mattered. Private Cole, who had found the abandoned Panther in the Normandy ditch in June 1944 and climbed up to look inside, went home to Ohio after the war and worked as a mechanic for 30 years. He never wrote about the Panther. He mentioned it occasionally to his son, the size of it, the quality of the optics, the way the engine had died from a leaking fuel line before a single American shell had touched it. He always ended the story the same way. "Hell of a tank," he would say. "Didn't work, though."